So, a key idea um, when trying to evaluate integrals when the arguments don't match is that you want to somehow break them down so that the arguments can match with one another. And so the problem that we're dealing with suggests the double angle identities, but the double angle identities can also be rewritten using, I think, what's usually called the half angle identities. So let me show an example of what I mean here. Like this part of the double angle identities here, you can solve for sine squared, and if you do that algebraically, I'm going to write x instead of theta, just because my thetas look bad when I draw them. Let's see, subtract 1, divide by negative 2, so that would be 1, so it would be 1 subtracted by cosine of 2x over 2. Okay, so I've just rearranged this double angle identity so that I solve for sine squared. You can do the same thing for this one. You can rearrange so that you solve for cosine squared. Oops, and it'll be 1 plus cosine 2x over 2. Okay, so yeah, when evaluating this integral, since the arguments don't match, we've got to do some sort of double angle identity or half angle identity reduction. So that means we want to evaluate the indefinite integral. Let's use our substitution that we just worked out over here. That this is going to be, actually, is there, no. Yeah, because the rule of thumb you want to have is that eventually we want to try to make the arguments match if we can, but we also want to keep reducing the powers. Because if we keep breaking it up into several different terms, then the linearity property of the integral operator can apply. So this is 1 minus cosine of 2x over 2. That's what sine squared is going to be, but watch out with cosine squared 2x. That's, when we apply that formula, it's 1 plus cosine of 4x, right? Because in my formula, the formula is for just 1x, and you would double it, right? So if it's 2x, you've got to double it to make it 4x over here. And then we can factor out that 1/2. So this is 1 minus cosine of 2x. So that's good. We've broken it up. That's a terrible integral though, huh? We've broken it up so that the linearity property of the integral operator could happen here. We could break it up into two separate integrals, except we have right now, we're multiplying by this. So we can't break it up yet. So to help us try to break it up, let's multiply these two parentheses to each other, okay, using FOIL or whatever you want to call it. So when we multiply 1 times 1, that makes 1. Multiply 1 times cosine 4x, that's going to make cosine of 4x. And then we multiply negative cosine of 2x times 1, that makes negative cosine of 2x. And then when we multiply negative cosine 2x times cosine of 4x, it's going to make negative cosine 2x cosine 4x. Respect to x, okay? So it's getting bigger, but this is good because now we can start evaluating some integrals. The integral of 1 is just x, so don't forget to distribute the 1/2. So I did this. I evaluate the integral of 1 with respect to x, and then I can evaluate this integral because everything's being separated, by a plus or minus, so they're different terms. So the antiderivative of cosine of 4x, we can remember the chain rule. So this is going to be the 1/2 that came from out here, and then we want to multiply by 1/4, and then that's sine of 4x. So if you're wondering where the 1/4 came from, it's because when I was thinking about the antiderivative, I know the antiderivative of cosine is sine, but because if you were to take a derivative here, a 4 would come out, and it's not supposed to be 4 cosine 4x. It's supposed to be just cosine 4. So the 1/4 compensates for that. So we've done the integral here. Now we need to do the integral of this. Similarly, that's going to be 1/2 from outside times another 1/2 when evaluating this antiderivative, and that's sine 2x. And we're almost done. Now we just have to do kind of a tricky antiderivative here. So before we do that, let's just write that out as minus 1/2 the indefinite integral of cosine 2x cosine 4x with respect to x. I need more room. So we're almost done. We've got all of this done. When you try to evaluate this antiderivative over here, since everything's now to the first power, then if we could just have one of these things be sine and the other thing be cosine, then we could use a u substitution. So since, let's see the formula we have. It's going to be sine squared. Yeah, that'll work. Okay, so here, let's take this. And it's still minus 1/2. And it's the integral. If I could just let u be sine squared x of some sort, maybe with some coefficients different, I know the derivative of u, the 2 would come down. So the derivative of sine squared x would be 2 sine x, and then the derivative of the innermost function, derivative of sine, would be cosine x. So maybe I can rearrange and rewrite either this or this so that I have a u and a du. Oh, except I think the one we need is so instead of letting u be sine squared x, let's u be sine of x, and then du is much simpler. That's just cosine of x. Because we can get that here, we can use one of our double angle identities to reduce that to have 2x in the argument. So we're going to keep cosine 2x, but then the cosine 4x, let's rewrite that as 1 minus 2 sine squared 2x. Okay, and so the reason where I'm getting that from is this last double angle identity. That way I have a sine involved, and that way I can let u be sine of 2x, and so the derivative of u is going to be 2 cosine 2x. Okay, the derivative of u is 2 cosine 2x, so I've almost got that out here. I just need to put a 2 in here, which means I need to factor out another 1/2 on the outside here. So this is negative 1/4 the integral of, this is our du, so I'm going to put that in the back. This is 1 minus 2 u squared du. And so that's an antiderivative we can evaluate, right? Because that's, again, we can use the linearity property. So all that substitution's done. So negative 1/4. This is antiderivative is going to be u minus antiderivative of 2u squared is 2 over 3 u to the third. And you need to plug in u equals sine 2x back in for u, 1/4. So this is sine 2x minus 2 over 3 sine to the third 2x. And then there's plus some constant c, but we would have that for all the other antiderivatives we evaluated here. Put it all together. This was our antiderivative. All these terms and then this we evaluated to be this over here. So if we don't see that in multiple choice, it's because this, you could use power reduction on this a few times, so you should get sine 6x in there at some point with a different coefficient. Pretty huge problem though, right? So if it's multiple choice, you still got some rearrangement to do there, but hopefully these terms help you eliminate some of the other choices so you don't have to do all that brutal algebra.